In this video, we will look at the concept of analyzing urban networks. Network analysis methods can be used to analyze many different types of networks. The concept of a network is abstract. It consists of a graph of nodes connected by edges. The nodes and edges can represent different types of things. Many of the network analysis methods were originally developed for analyzing social networks. In such networks, the nodes usually represent actors in some complex system, such as people, and edges represent relationships between those people. The image shows a social network diagram displaying friendship ties among a set of Facebook users. Urban networks in the city can also be represented abstractly as networks of nodes and edges. Cities typically contain many different types of networks. For example, street networks, transport networks, and pedestrian networks. Typically, networks are represented in 2D, on the ground plane. For example, network nodes can represent street or path junctions, and network edges can represent the center lines of streets or paths. In such representations, the actual geometry of the street, such as street widths, are not represented. Note that the methods developed by space syntax take a different approach. We will briefly highlight some of those differences in a later video. Next, we will clarify the difference between topology and geometry. Networks can have topology and geometry. Topology defines the connectivity between the nodes, but ignores any spatial location that those nodes may have. Consider the two examples shown in the diagram. From a topological point of view, the two networks shown are exactly the same. For certain types of networks, only the network topology is significant. For example, the previous example of friendship ties between Facebook users may ignore any location information about those people. In some cases, the geometry of a network can also be significant. The two networks shown have differing geometry, since the distances between the nodes have changed. Key dimensional values can be extracted from the geometry of the network. Most often, the length of the edges is significant. And in some cases, the angles between edges may also be significant. Next, let's take a closer look at network edges. Network edges capture an abstract relationship between two nodes. As such, they are usually represented by straight lines. They can either be directed or undirected. If edges are directed, then the connectivity only exists in one direction. In this case, they are usually depicted as an arrow. In the example, there is an edge from node A to node B, but there is no edge from node B to node A. In a directed network, two-way connections can still be represented using two edges. In the example, we can now see that there are two edges in opposite directions. Directed and undirected edges can have weights. The weight defines the cost of traveling along that edge. The default weight for an edge is typically 1. If all edges in a network have a weight of 1, then the cost of traveling down any edge is the same, irrespective of edge length. Custom weight can be assigned to edges, depending on the type of network. The weight may be calculated based on the edge length. For example, an estimate of travel time could be calculated based on the distance. Finally, let's briefly look at network representations using polylines. A path connects to nodes via a set of edges. In the example, there is a path from node A to node C, via node B. If there exists a path between two nodes, then those nodes are connected. For example, node A and node C are connected, but node A and node D are not connected. A component is a set of nodes that are all connected to one another. In the example, there are two components.
One has nodes A, B and C and the other has nodes D and E.
If all the nodes in a graph are connected, then the graph is a connected graph. Such a graph will have just one component. If a graph contains some nodes that are not connected, then the graph is a disconnected graph. Such a graph will have more than one component. The diagrams show a disconnected graph with three components. In order to be able to perform network analysis, the network first needs to be represented in some way. Urban networks are typically represented geometrically using a set of connected 2D polylines. However, most modeling systems will require polylines to have vertices at all intersection points. In the example, two polylines are shown, intersecting one another. In the top diagram, neither polyline has a vertex at the point of intersection. As a result, there is no path from node A to node B. In the bottom diagram, if both polylines have a vertex at the point of intersection, then it becomes possible to create a connection. Once such a connection is created, a path will exist from node A to node B. Here is another example, highlighting the fact that both polylines need to have a vertex at the point of intersection. In this case, we assume that the aim is to create a T-junction. In the top example, the horizontal polyline does not have a vertex at the point of intersection. As a result, no connection can be created. In the bottom example, the horizontal polyline has an additional vertex at the point of intersection. This allows a properly connected T-junction to be created.